as it refers to the GTR testers, the differential pressure method for testing OTR, which is an alternative to the coulometric, and it is a testing method where Labthink excels and has a big and impressive line of testers to present. We're going to start by sharing with you a quick presentation on a differential pressure method and the way a tester measures the oxygen permeability. After that, we're going to have the opportunity to see a quick demonstration from our laboratory here in Neusenburg in Germany of the C1068, our newest and top of technical quality tester. So I will not lose more time, and I will ask Mr. Martin Bryant, the sales director of Labthink International, based in Boston, to give us the presentation. Thank you very much once more.
Thank you, George. Thanks for the introduction, and thank you everybody for joining. It's nice to see so many people from so many different places with us today. Just one thing, in case any of you are still connected to audio live, if you can mute your microphone so that we don't suffer any interference or feedback or anything during the presentation. And at the end of the presentation, there'll be an opportunity to ask questions. So if you could save your questions for the end, or if you prefer, you can use the chat feature on Zoom to post the questions in there, and at the end of the webinar we will attend to the questions in the chat. So to get started, I'm going to share my screen with you, and as George says, today we're going to be talking about the manometric method of gas permeability testing, or gas permeability analysis or measurement. And this, as we know, is an alternative method for measuring oxygen transmission rate, amongst other capabilities. So today's talk will be divided into three sections. To start with, I'm going to give you an introduction to ASTM D1434, which is the standard describing the method of gas permeability measurement using differential and volumetric pressure. And we're going to take a look at some of the advantages that this method can provide under certain circumstances, and then finish with a comparison of the manometric method gas permeability testers. So let's look at the standard to start with. In fact, there are two major standards. One is ASTM D1434, and the other one is the international standard 15105 Part 1. And ASTM D1434, its official title is the standard test method for determining gas permeability characteristics of plastic film and sheeting. It's a very old standard. It was the first official standard for measuring gas permeability, and it's been renewed year after year, the most recent reapproval in 2015. And it covers methods of estimating state rate of transmission of gas through plastics in whatever form of film, sheeting, laminate, or even coated papers and fabrics. There are two methods in the standard. One is the manometric method, which we'll be addressing today, and the other one is a volumetric method. So to look at the manometric method, there's several diagrams on the screen here. The photograph that you see there is taken directly from the ASTM standard, and it is the original apparatus designed for this method. And for you who are old enough or around my generation, and perhaps George, you might think back to your school days and look at this picture and think it resembles something that you may have done in physics or chemistry class. It's a very rudimentary assembly. Basically, it comprises of a test cell, which you can see beneath the photograph, in which the specimen forms a barrier between two parts of the cell, the upper cell and the lower cell. You'll see there that there is a depression in the lower cell for a piece of filter paper. And the filter paper is included because it performs an important role for some of the materials which are very thin and flexible, or they may be brittle and subject to perhaps cracking or damage during the test. The filter paper is there to support those kind of specimens to make sure that they don't move or become damaged during the test. And the other components we'll take a look at shortly, but as you can gather from the title, it's called a manometric method. That's because part of the apparatus consists of a manometer. So looking at the schematic and looking at the list of components that make up the system on the right-hand side, it's immediately clear that there is one piece of equipment in this which was unique amongst the measurement of permeation, or the equipment used to measure permeation, and that's the vacuum pump. You can see it's denoted by the letter A. Some of the rest of the components are common with most permeation measurement systems. We have a cylinder of gas, which is for the test gas, the test cell, which I mentioned. Because we're using a vacuum pump, we're also required to have a vacuum gauge. There's a trap, a barometer to record the atmospheric pressure, an optional automatic recorder, or at least the automatic recorder was optional in the days when the standard was first developed. And then we have, in the pure and simple system, a mercury manometer. And then there is also a needle valve to control the flow of the gas. So as you can see, it's a relatively straightforward and simple principle. During the test, with Think equipment, we're able to plot the increase in pressure versus time, and also look at the gas transmission rate versus time. And so why do we look at the pressure? Well, the way that the system works is that the test cell is divided into two halves. And so the first part of the test procedure is to evacuate the lower cell. And this can take several hours. It's required to go to a very high level of vacuum. Once that's achieved, then we evacuate the rest of the system. And then once the test gas is released into the system, what we're looking at is a change in pressure in the lower cell. So as the gas moves into the evacuated chamber, the pressure therein starts to rise. And so we look at that rise, and when the rate of pressure change is consistent or the same, and on the drawing on the left, you can see there when the line becomes a straight line, that's when we determine that the system has reached a steady state. And likewise, on the drawing on the right, you can see that the GTR increases over time until it reaches a period where it flatlines or is in a steady state. And that's where we take the permeation measurement or the gas transmission rate result. So reading the standard, it describes in some detail lots of things which can affect the result. And so like any scientific measurement, it's important to be consistent and to rule out as many conditions which would perhaps affect the result in an adverse manner. And so some of the things which the standard addresses are, the need for very good valves. There is a need for a vacuum gauge so that we can monitor the progress of the evacuation. Of course, there's a vacuum pump involved. The effectiveness of the pump can also have an effect on the end result. It's very important to have a good seal, as with all permeation measurement systems. So the importance of the O-rings is stressed. And we need a pressure gauge because during the test, when the test gas is released into the upper cell, we want to make sure that the pressure is maintained at constant rate of pressure. So we don't want a system where the pressure is fluctuating, because that will also affect the result. And so it's important to have an accurate and precise pressure gauge to monitor the pressure and feedback to the system. And of course, some other factors are present, for example, the quality of the sample, the sample's nature, the presence of the filter paper, and the condition of the surfaces of the test cell, so that they mate together and form an effective seal. Excuse me, I think we missed one. So in this stage of the presentation, let's take a look at some of the comparison features of manometric and coulometric methods. So the coulometric method, most of you will know if you've been measuring oxygen transmission rate, is a very popular method for OTR measurement. It has its own ASTM standard, it's D3985, and we're also going to compare with the manometric method 1434. So one of the big differences between these methods is that the manometric method is capable of measuring the permeation characteristics of materials subject to a variety of different gases, whereas the coulometric method, it employs an electrical or electrochemical sensor which is specific for the measurement of oxygen. And so while it's a very good method for measuring oxygen transmission rate, it's of no use for measuring other gases according to standard 3985. And so the big difference is that ASTM D1434 manometric method can measure multiple gases. We'll also see in a minute that it has a very wide pressure range, whereas the coulometric method has a pressure range of is limited to 1 atmosphere. And the manometric method, it has a very wide measurement or test range, and this is partly to do with the choice of the sensor. So the coulometric sensor, being an electrochemical sensor, it responds to the number of oxygen molecules which pass over the sensor. And in doing this, it's partially consumed. So the longer that the sensor is in use and the higher the concentration of oxygen that passes over it, the shorter its lifetime will become. So it wouldn't be unusual to replace a coulometric sensor perhaps every 4 to 5 years or sooner if you were exposing it to high concentrations of oxygen. And so generally speaking, the range is limited so that we can avoid over-ranging the sensor and preserving its life. So it's common for coulometric sensor-based instruments to have an upper limit of 200 cc's per meter squared for 24 hours. With the manometric method, because we're not using a consumable sensor, this method employs very sensitive differential pressure transducer. The pressure range can be very, very wide, and so it's possible to measure both high barrier materials, or those with very low transmission rates, and very poor barrier materials, or those which have very high transmission rates. And so with no consumable sensor, there's considerable advantage, not only from its test capabilities, but also due to the life and maintenance costs of the equipment. The coulometric sensor is one of the most expensive components of an OTR tester following D3985. And so it contributes considerably to the cost of ownership. Also, this method has no carrier gas, so we don't require any nitrogen gas, unless, of course, you're using nitrogen as the test gas. With coulometric method, you require 2 cylinders of gas. One will have your oxygen in it, and the other will have a nitrogen carrier gas, which will sweep the cell and pick up any oxygen molecules and carry them to the sensor. And so we can look at the gas consumption, and immediately it's clear that the amount of gas required for the manometric method is lower, but it's actually lower on 2 counts. So it doesn't require the carrier gas. So that's one big gas consumption saving. And also the amount of gas required in the test is very, very small, much smaller than the amount of gas that would typically be used in a coulometric test. And then for scientists or chemists involved in the creation of new materials, the manometric method offers a few other advantages within its test results. So it can measure the gas transmission rate, or GTR, and the other method, coulometric method, measures OTR. But it also provides 3 important coefficients: the coefficient of permeability, the coefficient of solubility, and the coefficient of diffusion. Whereas with the OTR coulometric measurement, we get a coefficient of permeability. And the significance of these is that these measurements or these results are related to the actual chemical or physical properties of the sample or the specimen, whereas the GTR and the OTR are related only to the results obtained from that specimen. The coefficients of permeability, solubility, and diffusion are related to the barrier properties of the material itself. So an OTR result is specific to an individual specimen that is tested. And if I picked 3 specimens from the same source, it's quite likely that I would experience 3 different results. There may be slight differences in the OTR value, but the coefficients of permeability, solubility, and diffusion will be the same. And in that way, it's very useful for research and development specialists to analyze the properties of new materials. There's another difference which I'd like to point out between the 2 methods. So as I said, the manometric method, it doesn't use any carrier gas. And so if we compare the diagram on the left to the diagram on the right, you can see that in the right-hand side picture, there are some black molecules representing nitrogen. And so in this process, you have nitrogen flowing into the cell on the bottom and picking up the oxygen molecules and leaving on the bottom to the left side. And on the top, you have oxygen coming in and oxygen and nitrogen leaving on the top. And the reason for this is that the process of permeation follows the principle of molecular movement from a high concentration site to a low concentration site. And so on one side, you have a high concentration of oxygen, that's your test gas. And on the other side, there is a high concentration of nitrogen, that's your carrier gas. And so the propensity is for the oxygen to move from the upper side to the lower side. But in the same principle, you have this high concentration of nitrogen on the lower side and none on the upper side. And so there is the capability or the principle of permeation to take that nitrogen from one side to the other. And so through the specimen, as the molecules are diffusing and moving around inside the specimen, you have nitrogen molecules mixing with oxygen molecules. And so there is a capacity for some interference to occur at that point where you have the molecules mixed together. And the extent of that interference depends upon the specimen and the gas that's being used. And it's not clear exactly to what extent that interference can influence the result, although I have some data which is not included in the presentation today, which shows that there is a result depending on the gases concerned. Whereas if we look at the manometric method, because there's no nitrogen carrier gas involved, the permeation process can only move in one direction. It can only move from the oxygen or gas test gas side, which might be oxygen, nitrogen, air, it could be helium or whatever, to the vacuum side. So it's a true measurement of permeation in only one direction. So we can be certain that there is no interference from any kind of cross permeation within the specimen due to the presence of another gas. So in part two, let's consider some advantages. As I said, various gases can be used, so it's good for measurement of oxygen transmission rate, carbon dioxide, helium, nitrogen, and any other non-corrosive or non-explosive gas with applications for testing things such as medical packages, modified atmosphere packages. We've had a lot of success with introducing this method to manufacturers of tires and the components for tires, Saran wrap or food preservative cling film type products, some electronics. Aerospace is another interesting field of application where people are looking at different methods of transportation or scientific data gathering and looking at using vehicles such as balloons or airships, and clearly the permeation of the test gas, for example helium, through the special fabrics and textiles used in those products is of interest to those customers. We can also adapt the equipment to handle the testing of flammable and explosive gases, for example, hydrogen and methane. This would be of particular interest in the chemical industry and increasingly in the transportation industries with aerospace products, and more with hydrogen fuel cells for automotive applications. So in theory, this method can be used to test any kind of gas. We always stress for those customers that would be interested in testing flammable explosive gases that we need to very carefully consider the application and the test conditions, and then propose a specially designed piece of equipment for that application, because we want to make sure that the components used in the construction of the instrument are intrinsically safe or resistant to corrosion, and so on and so forth. And so it's very important to take into account the application during the design of the equipment, but it's possible. So earlier on, I told you that there is a wide range available within the manometric method. So with our equipment, the test cell has a standard volume. It's a very small test volume, and it's capable of measuring from 0.05 cc's per meter squared per day or per 24 hours per atmosphere up to 50,000. And so you can see with one instrument, you have the capability of measuring relatively high barrier materials, or those with a very low transmission rate, and very poor barrier materials, or those which are designed to have a high transmission rate. So it's good for a lot of different applications. Furthermore, the design of the cell is such that you can extend the volume, which will give the test cell the capacity of handling up to 500,000 cc's per meter squared, 24 hours per atmosphere. So with the extended test cell, it's very good for testing things like textiles and such like, which are by their nature porous, as well as high barrier materials like certain types of plastic film used in the packaging industry. So some people tend to refer to this manometric method as a research and development method for the reasons which I previously explained. You can gather an awful lot of important data from using this manometric style equipment, such as those coefficients of solubility, diffusion, and permeability that I mentioned. And by interpreting this data, you can determine whether the material that you've been designing is a good or high barrier. For example, if the solubility and diffusion coefficients are small, especially when they're both together small, that would indicate to you that the material is a good material or good candidate for high barrier applications. And so for this reason, this method is very suitable for research and development of new materials. Some people also refer to it as a scientific method, and that's because you'd need to go and look at how the study of permeation has developed. So right at the very beginning, I mentioned to you that ASTM D1434 is the first standard for measuring gas permeability through different materials, and subsequently ASTM D3985 was developed. And the reason that it was developed was at the time that you could see from that photograph I showed you that the apparatus is very crude, requires a lot of manual intervention from the operator and scientists, which is who is running the testing. And so D3985 was developed specifically for the measurement of oxygen, that being the most common concern for people who are testing products for food packaging. And so it was designed to make the process much easier to measure and much easier to use, less operator intervention, much more automated, and so on and so forth. And the difference is that one is a true sensor-based system, which is the coulometric. It relies on the coulometric sensor, whereas the other one is a scientific method. It follows established laws of gas physics, and so it's a very traceable method. In fact, if you study the standards in the standard D3985, the coulometric method, it goes on to explain in there that the material that was created in order to verify the coulometric OTR measurement method, there's a material at the time available from NIST or NIST, and that material was measured using the manometric method. So the material which was used to verify the accuracy and efficacy of the coulometric method was actually created and measured using the manometric method. And the conclusion of the authors of the standard is that the manometric method and the coulometric method, there is a high degree of correlation between the two methods. So although D3985 has gained popularity as a go-to method or main method, if you like, for measurement of oxygen transmission rate, it is acknowledged that the results obtained from the manometric method may be compared with those obtained from the coulometric method. And our own experience of this is proven in the fact that we take part in several independent interlaboratory or round-robin studies every year. And one of those studies involves the measurement of specified material under specified conditions for oxygen transmission rate. And some of the equipment that is used or participates in those studies is some of the manometric Labthink instruments. And so those results can be independently compared to the results obtained by following the coulometric D3985 method. I hinted that there is some cost effectiveness of following manometric method. On the equipment acquisition side, it's possible to get one piece of equipment with multiple capabilities. So for example, if you want to measure oxygen, nitrogen, carbon dioxide, or even helium, one piece of equipment will be capable of performing all measurements. So it's not necessary to have a dedicated OTR tester and a gas permeability tester. One piece of equipment could be eliminated and you can test OTR as well as other gases. The lower maintenance costs are there in the fact that the sensors are much less expensive. There's also less gas required, as I mentioned. This can streamline purchasing process. You only need to get one piece of equipment from one source. And you can make the point that it's slightly more environmentally friendly because less gas is being used. And so if you look at the environmental consequences of producing and using the machine, it's using less resources. So in part 3, I'm going to take a very, very brief look at some of the different equipment that we produce that can help you with this method. Let's look at the test principle first. I did mention how this works earlier on, but you can see here's the schematic of the equipment. Clearly, we need the gas cylinder. This could be oxygen or nitrogen or helium, for example. And there's a pressure gauge to make sure that the gas is being delivered at the correct pressure, a valve which will be able to release the gas into the test chamber. Item 8 there is a gas storage chamber. This is there to make sure that the gas is maintained at a constant pressure throughout the process. So we don't want the pressure varying. Test specimen is item 4, 5, and 6 are the 2 parts of the chamber. 7 is indicative of the gas molecules. 9 is the pressure sensor in the lower side, which detects the rise in pressure as the permeation process proceeds. And then number 10 there is the vacuum pump. And so the vacuum pump's purpose is to make sure that the system is primed prior to commencing the test. So the lower limit is 0.05 cc's per meter squared per 24 hours per atmosphere with a resolution of 0.001. The vacuum resolution, this is interesting. Its accuracy is plus or minus 0.2% with a resolution of 0.01 pascals. And the choice of the vacuum pump and the design of the system is very important. So because the equipment is capable of measuring high barrier materials, in other words, those which permit the transmission of very small amounts of gas, it's very important to have a vacuum system that can create an environment which is free as far as possible of any trapped or residual gas from a prior test. And so when testing the high barrier materials, it's very important to get a very high degree of vacuum. And it's very important that the system is designed in such a way that no residual gas has adhered or stuck to the internal bore of the pipes used in the design of the system. And so the high vacuum level is there to make sure that we remove as much as possible any residual gas, even a few molecules of gas which are stuck to the side of the pipe should be removed if possible. Temperature, its kind of resolution is kind of similar to what you would expect, resolution of 0.01 degrees Celsius with a plus or minus 0.15. And then we also have specifications for humidity control. Now, one thing you will note if you look into this for yourselves, or perhaps you already know it, is that the standard conditions for ASTM D1434 are for those of using a gas with 0% relative humidity in the system. And so in other words, the gas used or specified in 1434 is generally dry gas, and so there's no need for any humidification. But as I mentioned, this is a research and development method, and so some people, some scientists or customers would be interested in the effects of humidity on transmission rate, and so some of the equipment that we offer has the option of a humidity generator or humidifier to create those conditions of humidity. And these factors or features altogether contribute to the high accuracy of the test. So the equipment is, for the most part, very highly efficient, fully automatic testing. Some of the equipment has automatic sample clamping. Depending on the amount of testing required, customers can choose from analyzers which have 1, 3, or up to 6 test cells or chambers, and because the equipment is very versatile, there are different modes of operation. So the quick mode is basically you would just tell the instrument what temperature you want to run the test, and put in some other choices of what test cycle type you're going to follow. But basically, you literally only have to put in 1 or 2 parameters and press the start button, and everything else is fully automatic. And then there is a mode which we call expert scientific mode, where you can control the temperature. If the equipment is equipped with a humidity generator, you can control the humidity conditions. You can control the zero and the purging times, the preheating, whether some other features such as compensation are involved, and so on and so forth. So in summary, the operation of the equipment and the choice of the method can be as simple as you want it to be, or as complex as you want it to be, given the circumstances that you're trying to evaluate. Of course, like every system, it has to be reliable. That's why I say, the pipeline design inside the equipment has been designed to be as optimal as it can be. And I mentioned to you that it's stainless steel piping. The internal bore of the pipe is highly polished, so that there is little chance of any residual gas molecules sticking to the sides after the test is over. And in fact, during the test, we want to make sure that all the gas that breaches the specimen is measured. And for this reason, it's important that we use very high quality, internationally recognized brand name components in the system. So not only do we have the expertise within the company to design the system, but we also rely on the expertise of internationally known companies to provide us with high quality components, which we incorporate into every design. Oops. So there are several different models. I'm not going to go into too much detail about these. I believe George is going to show us one piece of equipment at the end of my talk here. But moving from the left to the right, we have a 6-cell machine. This is capable of the common range of 0.01 to 50,000, so a little bit higher than the standard range of sensitivity. Has 6 test cells based upon the use of an internal computer and a Windows tablet interface. And then we have model C130H. This has 3 test cells with pneumatic clamping in a horizontal arrangement, also very sensitive, 0.01 to 50,000. It uses an internal Windows computer and is controlled by an external keyboard, monitor and mouse. And then we have one of the very basic instruments. This is a single cell unit, C101H, which has an integral user interface, only 1 test cell, but high accuracy. My favorite, VAC V2. This is a very popular instrument, and the company has had a lot of success with this instrument in research and development institutes and academic environments are very, very easy to use, very versatile. It has a couple of unique features on it, one of which is something which we call data curve fitting. And so although the temperature control device, which you can see on the left there, is a circulating water bath capable of heating the machine up to 90 degrees Celsius, the data curve fitting function enables us to take 3 measurements within the standard range of temperature control. So we take those 3 measurements at some 3 points up to 90 degrees centigrade. And from those measurements, the machine has some very clever software inside which will calculate, based on the results of those 3 measurements, what the GTR would be at elevated temperatures beyond the measurement range of the temperature control. And so with that, we can predict what the GTR might be, for example, at 200 Celsius or 300 Celsius. So again, this consolidates its status as a great instrument for research and development. And then on the end here, the last one is VAC V1. This is a single cell unit with temperature control. You can see again there that it has an external temperature control device with circulating bath. Not to go into too much detail on this because there's a lot of information on here. I think I've covered most of it. For example, the control systems, the temperature ranges, test ranges we looked at. Here are the temperature ranges. So you've got up to 50 Celsius with the 2 sort of standard instruments, a 6-cell and a 3-cell there, and then with the VAC V2, because it has the circulating bath, it has a wider range of temperature control, down to 5 and up to 90, 95 degrees. Same with VAC V1, and then you have going to the more basic instrument 101H. It's 15 to 50. 4 of the instruments have the option of humidity control. The most basic one does not. Resolution is the same, and 2 of the instruments have pneumatic clamping, and the others are manually clamped. So we're getting towards the end now. So in summary, I'd like to point out that our company is very innovative. We have almost 100 patents in various countries around the world. Roughly 50% of those patents are related to the study of permeation measurement. Apart from the instruments that we've looked at briefly today, the gas transmission rate instruments, we have instruments for following the coulometric method, which we compared to today. We also have instruments for measuring moisture vapor transmission rate according to all applicable standards. And so with the lineup in our catalogue that we have now, we're very keen to talk to people about their needs for permeation equipment, because we have a very, very wide range which can meet all or most demands. And I think this positions us to be the new leader in this field of measurement. So with that, I believe that brings us to the end of the formal part of the presentation. I will hand over to back to George now, and we can look at any questions that you may have, or I think he may be ready to introduce us to a piece of equipment in the lab at our office in Frankfurt. So thanks for your attention, and I hope you found it useful. It was a pleasure to present to you today. So George, over to you.
Thank you, Martin. It was very informative. I enjoyed the presentation. And now we're going to have the chance to have a quick demonstration of our basic GTR permeation tester, C1068, by the technical director of Labthink GmbH. Alex, please, you can start showing us the features of the tester.
Yes, thank you, Mr. Todros. We're just trying to get the tester in the 6 testing cells. The access to them is really easy. So by pressing the button, we can access our samples. To open the cells, we release the pressure from them, and can you hear us? So have easy access sometimes to our samples. By pressing the button, we can open or close them. Closing the samples is being done in the same manner. Also, the is being controlled automatically. And sorry, we're having some small difficulties. We can continue. So, access to our samples is really easy. We can at all times release them, open them, and we can show you also how easy sample preparation can take place. So for this, we have our film here. We have the Labthink cutter. We set our cutter onto the film. So we're just preparing our sample. As you can see, it's already prepared. We will come to the fixing rings, and our sample is already done, already prepared. Coming back to the tester, like I was showing, we prepare them, we can release them. To fix our samples, we need to apply vacuum grease in the testing area. We are fixing the filter paper. We take our pre-made sample, we fix it here. We're closing the cells, and we are ready to go. To show you the user interface, so it's just going to be in this side. At all times, we can see for each cell the pressure that is inside the cell and the status in which each and every cell is currently being in. To start my test, after I prepared my samples, I quickly come to parameter settings. An important feature of the tester would be that I can actually deactivate some of the cells, and I could only work with the 3 from the left. So we have the freedom of also using just one cell, for example, or we can use all of them. Here in the right part, we can select the parameters that are general for the test, like the test temperature. We can set the pressure, so it's going to be an ambiental pressure. And then we can select and we can adjust the parameters for each and every cell. If we use the same parameters, so if, for example, if we want to test some reference film in all cells, I can just synchronize all of them. So then this means that for all cells, I have the same parameters. When I'm satisfied with the selection of the parameters, I just click set parameters, and this would be it. Right now, if we want to start the test, I will just simply press start all and everything will be fine. Also, you can also start and stop manually the cell. So you can just use, like I was telling you, blocks of 3 or only 1, and then you can manually start them from here. Another important thing is that at all times we can monitor the curves, so we can know what is happening and if the tester actually performs as it should. So we have access of the curves at all times. We can simply close it. And this would be quickly the presentation of our 106. Another important aspect is that for all tests that are started in history, we have a list with the reports. So the reports do not need to be manually saved. They are automatically being created and saved into the history of the tester. So the operators at all times, they know, and they can access their reports. Now, this would conclude the presentation of the 106. We're going to quickly close our cameras and we will show you the C1 of the 130. So this is the gas formation system. We call it, name is C130. The difference between them is that we only have 3 cells, so the capacity of the 3 cells. And one difference would be that, except versus the other one that has the tablet as a user interface, this has an embedded system, so we only need a monitor to we only need a monitor to control the tester. To access our cells, we simply press this button, and it comes out as a tray or not. If we have our samples, we simply include the filter paper to set up the sample, and we simply from here. Another important aspect I wanted to mention is that for the 3 cells, for the 6 cells, we have 3 or 6 manometric gauges. So this means that the reading takes place in the same time. So we don't have one singular sensor that does the reading. And with this, I would like to conclude our presentation for the testers. Mr. Kodros, thank you, everyone.
Thank you, Alex. Thank you for the presentation. We had the chance to check the 6 cells tester and the 3 cells tester. You are all welcome in our new laboratory and showroom in Neusenburg to come and visit us, take your own samples and come and test your films and your packaging. You are all most welcome. Now,